so we were in the middle of deriving these the columns of the stiffness matrix, and remember again the approach, right? We're assuming a displacement which extracts one column of the stiffness matrix, and then we can use our beam bending equations to get the forces, and you can see actually what you get there for the forces matches the stiffness values, okay? All right, so now let's do the second case to extract the second column. This is to get the second column. And this is going to be a displacement vector. Well, let's transpose it just so it's easier to write. Of 0, 1, 0, 0. So it just has a unit rotation, a 1 radian rotation around the first node. So if you look at that, granted, it's a really big rotation. I mean, but so be it. It's good enough for the derivation. So this node rotates at 1 radian and then comes back down and is fully fixed at this point. Right, so this is what we got. All right, and again, we have a force in a moment here, and also a force in a moment here. So when I put this in and multiply it by the stiffness matrix, I just extract the second row, which is the K1, 2, K2, 2, K3, 2, and K4, 2. And so that equals the right-hand side, which is F1, M1, F2, M2. All right? So in this case, this is F1. It's just K1, 2. M1 is K2, 2. F2 is K3, 2. And M2 is K4, 2. Those are the moments at that node. All right, we can still do sum of forces, so that gives us the sum of force equation, K1, 2 plus K3, 2. That has to equal 0. Sum of moments around A, so that gives us K2, 2 plus K4, 2 plus the force, K3, 2, 3, 2 times its moment arm, which is the length. So we're doing sum of moments around this point A. And then we also know the kinematic conditions. This is equal to 0. We know that the displacement here has to be 0. So this is sum of forces, sum of moments around point A. And then we can do also that the displacement at x equals 0 has to equal to 0. Going back to the equations we had before. So we're going to use this equation, all right? But we're going to put in different values for P and M. In this case, P is going to be K1, 2, and M is going to be K2, 2, all right? So we're going to get K1, 2 times L cubed over 3EI minus K2, 2 times L squared over 2EI has to go to 0 now because the deflection is 0, and now we have the rotation at x equal to 0 goes to 1. And so that gives me minus K1, 2 times L cubed over 3EI. And the next term is a plus K2, 2 times L over EI. That has to equal 1. All right? So those are the 4 equations. And now I'm going to solve those for K1, 2, K2, 2, K3, 2, and K4, 2. And again, I do that in Mathematica. Here's the 4 equations. We just solve them. So I don't screw up the algebra and make everyone go to sleep more than they are because of this. So this is kind of a long derivation. And so that gives us, just rewriting what I get here, you'll see it. This gives me that K1, 2 is equal to 6EI on L squared. K2, 2, this is the second column going down, is 4EI on L. K3, 2 is going to be minus 6EI on L squared. And then K4, 2 is equal to 2EI on L. All right, that's the second column. Now we go and do the third column. I need some more paper. Okay, so let's do the third column. Now to get the third column, right, we want a displacement vector as follows: 0, 0, 0, I'm sorry, 0, 0, 1, 0. So we just have a unit displacement on the right side. So it's going to look like this. All right. So this displaces by 1. We know the rotations are 0. Now, again, we do the same arguments. We multiply through, and this allows us to get that the up force is going to be the K 1, 3, K 2, 3, K 3, 3, K 4, 3. All right? And again, we do sum of forces in the Y. That gives me K1, 3 plus K3, 3 equals 0. Sum of moments. Let's do sum of moments. Let's do it so it's consistent. What did I do in Mathematica? I did sum of moments. K3 times L. So I did sum of moments around A again. So this gives me K2, 3 plus K4, 3 plus K3, 3 times L equals 0. And we also know now that the deflection at L equals 1. All right? So now when I do this, since the beam is flipped, I have to go back and look at these equations, right? Which are almost the same. It's just some of the signs have changed, okay? So in this situation, fold this up. If we're doing this one, here you can see that P is going to be K33 and M is going to be K43. So I can directly write this. This is going to be K33 L cubed on 3EI plus K43 L squared on 2EI. That equals 1. And then the rotation at L equals 0. So that's this equation. But again, P is going to be K33 and M is going to be K43. So, okay, where are we? So I got K33L squared on 2EI plus K43L on EI. And that has to go to 0, right? So those are my 4 equations. Again, we solve those for the 4 unknowns. That gives me K13 is equal to minus 12 EI on L cubed. K23 is equal to minus 6 EI. Now we're getting a lot of these, we know it's symmetric, so a lot of these match up with the other ones, but at least it's good to see it check. You know, it definitely should be symmetric. K33 is 12 EI on L cubed, and then the K43 is minus 6 EI on L squared. All right? And then the last one we do is the 4th column. And to do the 4th column, right? So here, the displacement vector is 0, 0, 0, 1. So that picture, we're fully fixed in on one side, and then on the right side, we have this positive rotation. So it has to be something like this. So it looks kind of like this. All right? And this is deflection is 0. All right? So this has a rotation of 1 radian, right? Remember, like the angles are always in radians, right? Okay, and again, when I plug this in, we can get the forces and the moments. All right, so in this case, it's going to be the 4th column. So this is K14, K24, K34, and K44. And now we go through the same equation, sum of forces in the y, K14 plus K34 have to equal 0. Sum of moments around A, K24 plus K44 plus K34 times L has to equal 0. And now the deflection equals 0, right? So we do the deflection at L equals 0. This is sum of moments around A equals 0, and this is sum of forces in the y direction equals 0. Okay, sum of moments, deflection at point L is equal to 0 in this case. So that gives me K34L cubed on 3EI plus M is K44L squared on 2EI. That has to equal 0. And then finally, that the rotation at L equals unity. And so putting that into the theta equation, that gives me K34L squared on 2EI plus K44L on EI equals 1. So now we solve for that. And again, I did that in Mathematica. Boom, there it is. Let's move it up. Right, here's the block here. That's the solution. And so that gives me, just to rewrite it, K14 is equal to 6EI on L squared. K24 is equal to 2EI on L. K34 is minus 6EI on L squared. And then finally K44 is 4EI on L. Okay, so that's all 4 by 4 elements or 16 elements for that stiffness matrix. Okay, so I mean it's a lot of algebra, but actually this trick of assuming the displacement and superimposing the responses is a nice way to do it. It's if you think about it, it is what the stiffness matrix does from the standpoint of it being an influence coefficient. Okay, so that's it. I hope that wasn't too bad, and let me stop right now. Okay.